Hello, welcome to my video. Today, we're talking about why data visualization is an absolute must for any data science project. Data visualization is like our secret weapon, it helps us see the hidden stories in data. It's not just about making pretty charts, it's about turning data into real insights. Whether you're a pro or new to machine learning, understanding data visualization is a game changer. It helps us find important patterns, tweak our models, and make smart decisions. So, if you're curious about why and how we need data visualization in the world of data science and machine learning, you're in the right place. Let's jump in. Installing and importing the libraries. Seaborn is a high-level Python data visualization library based on Matplotlib. So, in this tutorial, we'll be using Python 3 in Jupyter Notebook. Jupyter provides an interactive and versatile environment that combines code, text, and visuals seamlessly. Its support for multiple programming languages, like Python, and the rich ecosystem of libraries, including Pandas, Matplotlib and Seaborn, offer a powerful toolkit for data science project. First of all, we need to use pip to install the libraries including Pandas, Matplotlib, and Seaborn libraries for data visualization. Since they are already installed in my computer, I am not installing them again. After installation, then we can import these libraries with their corresponding aliases. Loading the dataset. Let's load a built-in dataset from Seaborn that contains physical measurements of 54,000 diamonds and their prices. Followed below is the data description for the variables. Then, we will briefly explore the dataset before we look into some of the important data visualization using Seaborn. Exploring the dataset. The df.shape attribute in Pandas is used to determine the dimensions of a data frame. It returns a tuple, representing the number of rows and columns in the data frame, respectively. This attribute is very useful for quickly getting an idea of the size and structure of the data. As we see, the data frame has a total of 53,940 rows and 10 columns or variables. Next, the df.info function is a method provided by the Pandas library in Python, and it is used to display a concise summary of a data frame's information. It provides useful details about the data frame structure, data types, memory usage, and non-null values. This summary is helpful for quickly understanding the characteristics of the data within the data frame. The df.describe function in Pandas is used to generate summary statistics of the numeric columns. It provides key statistical metrics that help to quickly understand the distribution and central tendencies of the data. The statistics returned include the count, mean, standard deviation, minimum, maximum, and the 3 percentiles. Next, the df.head function in Pandas is used to display the first few rows of a data frame. By default, it shows the top 5 rows, but we can pass an integer argument to specify a different number of rows to display. This function is often used to quickly preview the structure and content of a data frame. It helps to see a snapshot of the data at the beginning, which can be useful for understanding the column names, data types, and the actual values in the data frame. Next, let's briefly look at the categorical variables. This code snippet utilizes a for loop to iterate through a list of 3 categorical variables: cut, color, and clarity. For each variable, it calculates and prints the value counts within the dataset, providing valuable insights into the distribution of these categories. For example, there are more cuts for the types of ideal, premium and very good, ranging from over 12,000 to over 21,000 cuts, while the cuts for the types of good and fair are much less, only under 5,000 cuts. This information is valuable for identifying any imbalances or dominant categories. Next, finding missing values in Pandas data frame. In this code snippet, we're examining the missing data in our data frame df. To achieve this, we use the isNull.sum method, which calculates the number of missing values in each column, which allows us to quickly assess which columns have missing data and how many missing values they contain. It's an essential step in data preprocessing and quality assessment before performing any data analysis or machine learning. As we see, there is no missing data in this diamonds dataset based on its output. Now, let's start to create different charts for data visualization. Firstly, we start with bar plot. A bar plot in Python Seaborn library is a data visualization technique used to display categorical data using rectangular bars. It's particularly useful for comparing and showing the distribution or relationship between different categories of data. Each bar represents a category, and the height of the bar indicates the value associated with that category. This code is designed to automate the creation of multiple bar plots, one for each categorical variable in the categorical list, to visualize the relationship between each categorical variable and the price variable in the data frame df. It's a convenient way to quickly explore and compare how prices are distributed across different categories. Next, we're creating scatter plot. It is a powerful tool in data visualization for exploring relationships between numerical variables. Scatter plots help us understand how one numerical variable, on the x-axis, relates to another, on the y-axis, and can reveal patterns, clusters, or trends in our data. The code you see is designed to create a series of scatter plots to visualize the relationship between several numerical attributes, specifically x, y, and z, and the price of diamonds in a dataset. Each scatter plot compares one of these attributes to price and uses different colors and markers to represent different cut categories, allowing us to see how the cut of a diamond influences the relationship. Here's a breakdown of what the code does. Firstly, we specify the numerical attributes we want to investigate in the numerical 1 list and create a grid of 4 subplots, 2 rows and 2 columns, using matplotlib. Then, we loop through the numerical 1 list and, for each attribute, create a scatter plot using Seaborn. The x-axis represents the numerical attribute, the y-axis represents the price, and the points are colored and styled based on the cut category. Then, we set titles for each subplot to indicate which attribute is being visualized. Finally, we use plt.tight_layout to ensure that the subplots are neatly arranged. The two charts below are the scatter plots between the variable price and the variables and x. Likewise, these two charts are the scatter plots between price and the variables y and z. Next, we are delving into histograms. Histogram is another essential data visualization tool which helps us understand the distribution of numerical data by dividing it into bins, or intervals, and showing how many data points fall into each bin. This code is designed to create a set of histograms for several numerical attributes from our dataset. Let's break down what the code does. We've selected a list of numerical attributes to explore in the numerical 2 list. These attributes include depth, table, price, x, y, and z. Again, we set up a grid of subplots using matplotlib. We specify that we want 2 rows and 4 columns of subplots, resulting in a total of 8 histograms arranged in a 2x4 grid. The fig size parameter controls the overall size of the plot. We flatten the axis array to make it easier to loop through and access each subplot. The for loop iterates through the numerical 2 list. For each numerical attribute, it creates a histogram using Seaborn's histplot function. We specify the data frame df and set the x-axis to the current numerical attribute. We also use hue to color the bars based on the cut category, add a kernel density estimate curve for a smooth representation of the distribution, and specify the number of bins as 30. Then, a title is set for each subplot to indicate which attribute's histogram is being displayed. Finally, we remove the last subplot using fig.delAxis, axis-1, because there are only 7 numerical attributes in numerical 2, and our subplot grid is 2 times 4. This ensures a clean and organized layout. This code allows us to visually explore the distribution of various numerical attributes in our dataset. By using histograms, we can gain insights into the shape and spread of the data, identify potential outliers, and understand how the cut category may influence the distribution of these attributes. Next, let's explore line plot. Line plots are a valuable tool for visualizing the relationship between 2 numerical variables over a continuous range. It is particularly useful for showing trends, patterns, or correlations in data. The code you see is designed to create a series of line plots to visualize how certain numerical attributes relate to the price of diamonds in our dataset. As you see here, we've selected a list of numerical attributes to investigate in the numerical 3 list. These attributes include depth, table, x, y, and z. The for loop iterates through the numerical 3 list. For each numerical attribute, it creates a line plot using Seaborn's lineplot function. We specify the data frame df and set the x-axis to the current numerical attribute and the y-axis to price. A title is also set for each line plot to indicate which numerical attribute is being plotted against the price. This title helps us quickly identify which relationship we're examining in each subplot. This code allows us to visually explore how the values of these numerical attributes change concerning the price of diamonds. By using line plots, we can detect trends and understand how changes in one variable might be associated with changes in price. For example, in the charts below, based on the line plot between carat and price, it's evident that there is a positive correlation between the carat weight of diamonds and their respective prices. Overall, line plot is a valuable technique for uncovering patterns and relationships in our data that can inform further analysis or decision-making. Violin plot. In this code segment, we're creating violin plot, a fascinating data visualization technique that combines aspects of box plots and kernel density estimation to give us a comprehensive view of the distribution of a numerical variable within different categories. These plots are particularly useful when you want to understand how a numerical attribute, in this case, price of diamonds, is distributed across different categorical variables. Let's look at the code. We're using a for loop to iterate through a list of categorical variables, which we've stored in the categorical list. These categorical variables could be things like cut, color, or clarity, and we want to understand how they relate to the price of diamonds. For each category in the loop, we create a violin plot using Seaborn's violin plot function. The x-axis represents the categorical variable, for example, cut or color, and the y-axis represents the price of diamonds. The violin plot shows the distribution of prices within each category, providing insights into the spread and central tendency of prices for different categories. We set a title for each violin plot to make it clear which categorical variable is being analyzed in each subplot. These violin plots are fantastic tools for visualizing how the price of diamonds varies across different categories, helping us spot trends, differences, and distributions within our data. Now, let's look at box plot. A box plot, also known as a box and whisker plot, is a valuable data visualization technique that provides insights into the distribution, spread, and potential outliers within a dataset. These plots are particularly useful for comparing the distribution of a numerical variable, in this case, the price of diamonds, across different categories represented by categorical variables. Here in the code, we're using a for loop to iterate through a list of categorical variables, which we've stored in the categorical list. These categorical variables could include attributes like cut, color, or clarity, and we're interested in understanding how they relate to the price of diamonds. For each category in the loop, we create a box plot using Seaborn's box plot function. The x-axis represents the categorical variable, such as cut or color, and the y-axis represents the price of diamonds. The box plot displays key statistics such as the median, quartiles, and potential outliers for each category, providing a clear picture of how prices vary within different categories. From the three box plots below, we can visualize and compare the distribution of diamond prices across different categories. They help us identify differences in price ranges and potential anomalies within the data, which can be crucial for gaining insights into factors influencing diamond prices. Next, heat map. Heat maps can help identify patterns and relationships in the data. By using color gradients to represent data values, they make it simple to spot trends, clusters, and variations within the dataset. It is often used to visualize correlation matrices. For example, in the context of machine learning, you can use a heat map to quickly assess the pairwise correlations between different features in your dataset. This is crucial for feature selection and understanding the relationships between variables. In addition, heat maps can also be used for anomaly detection since it can highlight outliers or anomalies in a dataset. Unusual values often stand out as distinct patterns of color in the heat map, making them easier to detect. As shown here in the cell, the code uses Seaborn to create a heat map to visualize the correlation between a subset of numerical variables, numerical 2, in the dataframe df. It generates a heat map that provides a visual representation of the pairwise correlations between the selected 7 numerical variables in the dataset. It's a powerful tool for quickly identifying relationships and patterns between these 7 variables, which can be crucial for feature selection, identifying multicollinearity in regression analysis, and gaining a deeper understanding of the relationships within our data. The annotated values within the cells make it easy to interpret the strength and direction of the correlations. By visually representing these correlations, we can make more informed decisions and refine our data analysis techniques. Next, point plot. Now, we're introducing a point plot chart, which is valuable to showcase the relationship between categorical and numerical variables in our dataset. Point plots are excellent for displaying data points as individual markers, making it easy to understand trends, differences, and variations within different categories. In this code, we want to explore how the categorical variables, cut, color, or clarity, relate to the price of diamonds. For each category in the loop, we create a point plot using Seaborn's point plot function. The x-axis typically represents the categorical variable, and the y-axis represents the price of diamonds. Each data point is displayed as a marker. In this case, we use a triangle as the marker, and in green color. Point plots are fantastic for revealing variations in numerical values across different categories. They allow us to visualize the central tendency of the data within each category and identify any notable patterns or differences. This visualization can be instrumental in making data-driven decisions and understanding how different attributes impact the price of diamonds. Now, let's look at density plot. Density plots, also known as kernel density plots, rely on kernel density estimation, KDE, to visualize the distribution of data. KDE is a statistical technique that provides a smooth, continuous representation of the underlying probability density function of a dataset, allowing you to visualize the data's distribution without making specific assumptions about its parametric form. This makes KDE and density plots valuable tools in data visualization and exploratory data analysis. In this code, we want to visualize the density of diamond prices for different categories within cut, color, and clarity. The sns.dplot function from the Seaborn library is used to create these density plots. KDE is a non-parametric way to estimate the probability density function of a continuous random variable. In simpler terms, it helps us visualize how data is distributed along the numerical price axis for each category. The multiple equals stack parameter indicates that we want to create stack density plots for each category within the categorical variable. This means that for each category in cut, color, and clarity, a separate density plot will be created and stacked on top of each other. This allows us to compare the distributions of price for different categories effectively. By using density plots in this manner, you can gain valuable insights into how the distribution of diamond prices varies across different categories like cut, color, and clarity. You can visually assess if certain categories tend to have higher or lower price ranges and how they overlap or differ from one another. Likewise, from this code snippet, we're working with a list called numerical 1 which contains the features x, y, and z. For each feature, we're creating a density plot using Seaborn's KDE plot. This plot visualizes the distribution of price based on the selected feature. The x equals number 1 parameter means we're using the feature from numerical 1 as the x-axis variable, and y equals price specifies that price is the variable we're comparing it against. The hue equals cut parameter adds another layer of information by coloring the plot according to the cut variable, which can help us distinguish different categories. Additionally, multiple equals stack is used to stack the density plots, which can be helpful when comparing distributions. In essence, this code provides an insightful way to visualize how the price of diamonds varies concerning specific numerical attributes, x, y, z, while accounting for differences in the cut category. By examining these KDE plots, you can gain a deeper understanding of how these numerical attributes influence diamond prices and how they may differ across different cut categories. It's a powerful tool for data exploration and uncovering valuable insights in the dataset. Next, let's create count plot. A count plot is a type of categorical plot that displays the counts of unique values or categories within a categorical variable. They are useful for visualizing the distribution of categorical data and understanding the frequency or prevalence of different categories. In this loop, we're, again, using enumerate to go through each categorical variable listed in the categorical list. For every categorical variable, we're creating a count plot using Seaborn's countPlot function. The x equals cat parameter indicates that we're plotting the variable specified by cat on the x-axis. The data source for this operation is the data frame df. What this does is it provides a visual representation of how frequently each category occurs within the selected categorical variable. This can be particularly insightful for understanding the distribution of categorical data. Overall, this code is a valuable tool for gaining quick insights into the distribution of categorical variables in our dataset. It's a fundamental step in exploratory data analysis. Swarm plot. A swarm plot is a type of categorical scatter plot provided by Seaborn that is useful for visualizing the distribution of data points within a categorical variable. It is particularly valuable when you want to explore the distribution of data in a way that avoids overlapping points common in traditional scatter plots. Swarm plots distribute the points evenly along the categorical axis, preventing overlap and providing a clearer view of the data. In addition, swarm plots can reveal patterns or trends within the data, such as clustering, gaps, or skewness, which may not be immediately apparent in other types of plots. This code here utilizes Seaborn's swarm plot function to create a visual representation of the relationship between two variables, clarity and price, from the dataset df. It creates a swarm plot that shows how the price of diamonds varies with clarity, while differentiating the data points with an extra layer of information by coloring the points based on the cut category. Swarm plots are useful for visualizing the distribution and density of data points along the categorical axis, clarity in this case, and provide insights into the relationships between variables while considering the impact of another categorical variable, cut. Now, let's delve into pair plot. A pair plot, also known as a scatterplot matrix, is an important and useful data visualization tool provided by Seaborn. It's primarily used for exploring relationships between multiple variables in a dataset. A pair plot consists of individual variable distributions along the diagonal and scatter plots representing pairwise relationships elsewhere. It can be used for 1. Visualizing multivariate relationships. Pair plots allow you to visualize relationships between pairs of variables in a dataset. This is particularly valuable when you have a large number of variables, and you want to quickly get an overview of how they relate to each other. 2. Identifying patterns. They help in identifying patterns, trends, and correlations between variables. By examining the scatter plots, we can visually assess whether variables have linear relationships, nonlinear relationships, or no discernible patterns. 3. Diagnosing data. They are useful for data diagnosis and preliminary data exploration. They can help you spot potential outliers, clusters, or data distribution characteristics that might require further investigation. 4. Variable selection. In feature selection for machine learning, pair plots can assist in choosing which variables to include in a model. By examining relationships with the target variable or with other important features, we can make informed decisions about variable selection. This line of code here is to create a pair plot, as shown in the figure below, that visualizes relationships between 7 numerical variables in the data frame df, with different markers and colors, including O, S, and D, indicating different categories within the cut variable. This can be a powerful tool for exploring multivariate data and identifying patterns or correlations. Next, pair grid. Here, a pair grid is a concept related to the pair plot that we just talked about for data visualization, but they serve different purposes and are implemented differently. A pair plot is a single plot that combines both scatter plots and histograms for pairwise relationships between multiple variables in a dataset, while a pair grid is a more general framework for creating various types of plots in a grid layout. In other words, a pair grid is a versatile visualization tool provided by the Seaborn library that allows us to define the layout of the grid, specifying which plots go on the diagonal, upper triangle, and lower triangle. It also has the flexibility in generating plot types, where we can use different types of plots, such as scatter plots, histograms, bar plots, etc., in each subplot. This flexibility allows us to choose the most appropriate visualization for the data. The first block of code snippets creates a grid of subplots using pair grid. As shown in the graph, along the diagonal, it plots histograms of the 7 variables, while in the off-diagonal plots, it creates scatter plots for pairwise combinations of variables. The color of the data points in the scatter plots is determined by the cut variable. Finally, a legend is added to explain the colors. This visualization is effective for exploring relationships and distributions in multivariate data. Now, this second block of code snippets creates a grid of scatter plots with regression lines as indicated in the figures, for visualizing the relationship between the numerical variable, price, in y-axis and the numerical variables, caret, x, y, and z, in x-axis, with each plot colored by cut, which is a categorical variable. The y-axis limits and ticks are customized, and a legend is added for clarity. This visualization is effective for understanding how the price of diamonds relates to their carat weight and dimensions, taking different cuts into account. Now, let's look at Facet Grid. Facet Grid is a powerful visualization technique provided by the Seaborn library that allows to create a grid of subplots based on the unique values in one or more categorical variables. This enables to compare multiple facets of the dataset in a structured and organized manner. It can be combined with other Seaborn plot types like scatter plots, bar plots, and histograms to represent the relationships between variables within each facet. Facet Grid is a valuable tool for visualizing and understanding complex datasets, especially when we want to compare different categories or combinations of categories across multiple dimensions. In this code snippet, we're focusing on three categorical variables: cut, color, and clarity, as shown in the figures. The code runs a loop to generate separate visualizations for each of these categories. For each category, we're using a facet grid, which allows us to arrange multiple plots in a grid from the dataframe df. The called parameter specifies that each category will have its own column. We're also using color hue to differentiate between categories. Next, we're using sns.histplot to create histograms of the price variable. This will give us a clear understanding of how the price distribution varies across different categories. As you can see, this line of figures shows the price distributions across cut categories. Likewise, these two line of figures show the price distributions across the other two categories, including color and clarity. Next, let's delve into the joint distribution plot. The joint distribution plot in Seaborn is a crucial visualization tool for understanding the relationship between two continuous variables. It provides a combined view of the univariate distributions of each variable and their bivariate distribution. 1. Comprehensive insight. It offers a comprehensive view of both the individual distributions, histograms, and the joint distribution, scatter plot, of two variables in a single plot. This allows for a more holistic understanding of the data. 2. Correlation assessment. It helps in visually assessing the correlation or association between two variables. Patterns in the scatter plot can reveal if there's a linear relationship, clusters, or any other significant trends. 3. Density estimation. The plot includes a contour plot or kernel density estimate that provides additional information about the density of data points, giving a sense of where the data is most concentrated. The code snippet provided here is using a loop to create a series of joint distribution plots using Seaborn. Specifically, it's generating scatter plots with marginal histograms for different pairs of variables from the list numerical 1 against the price variable, with the points colored by the cut variable using the set2 palette. This code is effective for exploring how different numerical attributes relate to the price of the data points. This first figure displays the joint distribution plot between the numerical variables, carat, and price. And this shows the rest of three joint distribution plots between price and the three numerical variables, x, y, and z. Now, let's look at categorical plot or cat plot. In this plot, we're exploring the relationship between cut, a categorical variable, and price, a numerical variable. The x-axis represents the price, while the y-axis shows the different cut categories. The kind equals violin parameter indicates that we're using a violin plot, which combines elements of a box plot and a kernel density plot. This provides a comprehensive view of the data distribution and its probability density. This visualization can be incredibly useful in understanding how different cut categories impact the distribution of prices. It's a powerful tool for exploratory data analysis and can help uncover hidden patterns and trends. In addition, the catplot function has the ability to easily switch between different kind parameters so as to provide a versatile and powerful tool for data visualization. Now, let's switch to a box plot as demonstrated in this line of your code where kind equals box, instead of violin, which offers a different perspective. Box plots provide clear information about the median, quartiles, and potential outliers within each cut category. This can be particularly useful for identifying skewness, spread, and central tendencies within the dataset. By having the ability to easily change the kind parameter, you can efficiently explore and compare these different visual representations, which can lead to a more comprehensive understanding of the data. This adaptability allows you to choose the most appropriate visualization technique for your specific dataset and analytical goals. Lastly, we are going to create strip plot. In this snippet, we're iterating over a list of categorical variables, categorical, and creating a strip plot for each one. This means we're visualizing the relationship between the categorical variable and the price, with points along the y-axis representing individual data points. The hue parameter is set to cut, which introduces color differentiation for different cut categories. This allows us to discern how the price varies not only with respect to the categorical variable but also within different cut levels. As shown in these three strip plots, each of them offers a clear view of the distribution of price across different levels of the categorical variable, such as cut, color, or clarity. This approach can unveil patterns, outliers, and trends that might not be immediately evident in a tabular format. In the meantime, I would like to mention that you may or may not already notice the similarity between these three strip plots and the swarm plots that we introduced earlier. Both of them are similar in that they both display individual data points along one axis of a categorical variable. However, they differ in their approach to handling overlapping points. In a strip plot, data points are plotted as individual points, which means they can overlap if there are many data points with similar values. This can sometimes result in points being stacked on top of each other, potentially making it harder to discern the exact distribution of the data. A swarm plot, on the other hand, is a variation of a strip plot where the points are adjusted to avoid overlap. The points are spread out along the categorical axis, ensuring that they do not overlap with one another. This can provide a clearer view of the distribution of data points, especially when dealing with a large number of data points or when there is a high degree of overlap. In summary, strip plots and swarm plots are both types of categorical scatter plots used to visualize the distribution of data points within different categories. The choice between a strip plot and a swarm plot depends on the nature of the data and what you want to emphasize. Strip plots are simpler and more suitable for smaller datasets, while swarm plots are better at handling larger datasets with potentially overlapping points. If it's crucial to prevent points from overlapping, a swarm plot might be the preferred choice. Now, let's summarize it. In this video, we have covered 17 powerful data visualization techniques using the Seaborn library. Here's a quick recap. 1. Bar plot, effectively compare categorical data. 2. Scatter plot, explore relationships between two continuous variables. 3. Histogram, visualize the distribution of a single variable. 4. Line plot, track trends and changes over time. 5. Violin plot, display the distribution of data across different categories. 6. Box plot, summarize data's distribution and detect outliers. 7. Heat map, visualize complex datasets using colors. 8. Point plot, display point estimates and confidence intervals. 9. Density plot, examine the distribution of a continuous variable. 10. Count plot, display the frequency of observations in each category. 11. Swarm plot, visualize the distribution of categorical data points. 12. Pair plot, explore relationships between multiple variables. 13. Pair grid, visualize relationships for multiple variables. 14. Facet grid, create a grid of subplots based on a categorical variable. 15. Joint distribution plot, visualize the relationship between two variables and their distributions. 16. Cat plot, categorical plot, create various types of categorical plots. 17. Strip plot, display individual data points. Remember, choosing the right visualization technique depends on your data and the story you want to tell. So, explore these techniques, experiment, and find the best fit for your specific dataset. Happy visualizing and thank you for watching.